forget smooth runways and those long takeoff rolls. Today, we're skipping all that. We're going straight up.
Yeah, going straight.
You're diving deep into the world of helicopter flight controls.
Exactly. And, those agile, sometimes almost impossible-looking moves that helicopters pull off.
Right.
I think a lot of people look at that and think, like, how do they do that?
Yeah, how is that even possible?
Well, today, that's what we're going to break down for you, those elegant control systems that make all of that possible.
We've got some really cool source material here to help us with that excerpts that get down to the nitty-gritty of how a pilot commands these incredible flying machines.
That's right.
Our mission for this deep dive is to pull out the core wisdom, those aha moments about the three major controls and how they all work together.
Yeah.
And we want to do that without getting lost in too many technical details.
Absolutely.
Ready to take off.
Let's do it.
So let's start with the collective pitch control. And if you can picture yourself inside a helicopter cockpit,
right,
this is usually the lever that's on the pilot's left side.
Yeah, that's right.
Okay, so let's break this down. The collective. That word collective is key here because the single lever is changing the pitch angle of all the main rotor blades all at the same time and by the same amount.
Right.
So just as a reminder to our listeners, pitch angle is also known as the angle of incidence.
Yeah.
And it's basically the angle at which the rotor blade is meeting the airflow.
Right.
So think of it almost like adjusting the tilt of every single wing on top of the helicopter.
Yeah, exactly. Imagine each of the rotor blades as its own little airplane wing.
Yeah.
And so the collective is the way for the pilot to control.
Like all at the same time?
All at the same time.
Yep. Okay.
So pull the collective up, the angle increases. Push it down, it decreases.
Makes sense.
And here's the key. This change in the pitch has a direct impact on lift and drag.
Okay, so help me understand that, because as you increase the pitch angle, you're getting more lift, right?
Correct.
But you're also creating more drag, right?
More resistance against the airflow, exactly.
And what happens when the drag goes up?
Well, the RPM of the rotor, that rotational speed, tends to decrease.
And on the flip side, if you decrease the pitch...
there's less drag, and the RPM wants to climb.
Got it.
Yeah.
Okay, so the core concept here, the collective isn't just about going up and down.
Right.
It's a delicate dance between lift drag and the speed of the rotor.
That's right. A constant balance that the pilot has to maintain.
Got it. Okay, so that's the collective. Now let's talk about the throttle control, because this isn't always located in the same spot, is it?
Yeah, it's not.
Our source material mentions it could be a twist grip right on the collective lever itself.
Kind of like a motorcycle throttle, yeah.
Yeah, or it could be mounted overhead or even down on the floor in some helicopters.
That's right. But no matter where it is, its job remains the same to regulate the engine RPM.
How fast it's turning over.
Exactly. And generally speaking, twisting it counterclockwise increases that RPM, and twisting it clockwise decreases it.
Okay, so let's talk about how the collective and the throttle work together. Because when you raise the collective, you're demanding more lift, right? You're increasing that blade pitch.
Correct.
But the engine has to work harder to maintain that constant rotor RPM.
Exactly.
So the throttle needs to increase the engine power to keep up.
That's right. And then the opposite is true. If you lower the collective, you need less power, so you decrease the throttle.
Okay, so it's this constant balancing act to keep those blades spinning at just the right speed.
All time, yeah.
And our source material talks about governors and correlators.
Right.
And these are like little helpers for the pilot to manage that coordination.
That's a great way to think about it, yeah.
Can you break down for me what each of those does?
Sure. So a governor is a pretty sophisticated system that monitors both the engine and the rotor RPM.
Okay.
And if it detects any change from the rotor speed that the pilot has set,
right,
it immediately adjusts the engine power to correct it.
Oh, wow.
So you can kind of think of it like cruise control.
Okay.
But for your rotor speed specifically.
I like that analogy.
And these governors are common in turbine-powered helicopters and in some of the more advanced piston engine models too.
Okay.
And what's interesting is that it takes some of those really fine adjustments off the pilot's plate.
Right, so they can focus on the bigger picture.
Yeah, exactly. But of course, you still need to understand how all these systems work together.
Of course.
To fly safely.
So the governor's like the high-tech solution keeping everything in check.
Right.
So what about a correlator?
So a correlator is more of a direct mechanical link between the collective lever and the engine throttle.
Okay.
So when the pilot moves the collective up or down, the correlator moves the throttle too in a preset way.
Okay.
So it's kind of like it gives you a starting point for the power setting.
Okay.
But the pilot still has to fine-tune things using that twist grip throttles.
To get the RPM exactly right.
Exactly.
Got it. So the correlator gets you in the ballpark.
Right.
The governor parks you in the perfect spot.
That's a great way to put it.
And in helicopters without either of those?
The pilot is doing all that, manually coordinating the collective and throttle movements.
So it sounds like that demands a lot of skill.
It does. Yeah, you need very smooth, deliberate inputs on the controls.
Okay.
Any large or jerky movements can really destabilize the helicopter.
Right.
Smooth, coordinated movements. That's the key to precise, controlled flight.
Got it. And it's important to remember that while the collective is primarily how you control the manifold pressure,
which is essentially a measure of the air pressure in the engine's intake.
Okay.
And directly related to how much power it's producing.
Right.
And the throttle is the primary way to control RPM.
Right.
They do influence each other.
Of course.
It's a connected system.
So you've got to be aware of both the tachometer showing the RPM
Right.
and the manifold pressure gauge to really understand what adjustments to make.
That's right.
Okay, so we've talked about the collective and the throttle working together to manage that vertical movement and rotor speed.
Yeah.
Now let's talk about how you make the helicopter move horizontally. That's the job of the cyclic pitch control, right?
That's exactly right.
Yeah.
The cyclic is what gives you that directional control, flying forward, backward, left, and right.
And it's usually located between the pilot's legs or seats, right?
Yeah, it looks and feels a bit like an airplane's control stick.
Okay, so how does pushing that stick forward translate into the whole helicopter moving forward? Because it's not like steering a car.
No, it's not. It's not direct steering like that.
Right.
Instead, what the cyclic does is it tilts the entire main rotor's tip path plane in the direction you want to go.
Okay, and remind me what the tip path plane is.
So that's the imaginary disc that's created by the tips of the rotating blades as they spin.
Okay, got it.
So if you push the cyclic forward, the whole rotor disc tilts forward.
Okay, I can visualize that disc tilting, but how does this relatively small stick actually change the angle of that huge spinning rotor disc?
So this is where the really ingenious mechanics of cyclic pitch variation come in.
Okay.
Remember how the collective changes the pitch of all the blades at the same time? Well, the cyclic changes the pitch of individual rotor blades as they rotate.
Oh, wow. Okay.
But it does it differently based on where they are in the rotation.
Okay.
So, for example, if you want to tilt the rotor disc forward,
right,
as a blade comes around on the right side of the helicopter,
yeah,
the cyclic mechanism will decrease its pitch angle.
Okay.
Which means less lift on that side.
Okay.
And then as that blade goes around to the left side and retreats,
right,
its pitch angle will increase, generating more lift.
So it's a deliberate imbalance of lift across the rotor disc.
Exactly. More lift on one side, less on the other.
And that causes the whole disc to tilt.
That's right.
That's so cool.
Yeah.
But you know what? Our source material mentions this thing called the gyro effect. And mechanical linkages that have to compensate by like 90 degrees?
Yeah, that's an interesting one.
What's going on with that?
But because the rotor disc is spinning so fast,
yeah,
it acts like a gyroscope.
Okay. Yeah.
And it exhibits this phenomenon called gyroscopic precession.
Okay, I'm going to need you to break that down for me.
Yeah, so basically it means that if you apply a force to something that's spinning,
right,
the effect of that force isn't felt right at the point where you apply it.
Okay.
It's felt about 90 degrees later in the direction of rotation.
Oh, that's interesting.
Yeah. So to compensate for that, the linkages that connect the cyclic to the rotor blades are designed in a really clever way.
Okay.
So when you push the cyclic forward, the change in the pitch angle actually happens about 90 degrees before that blade reaches the forward position.
Oh, wow.
This ensures that the maximum downward deflection of the blade,
yeah,
which creates that forward tilt, happens exactly where the pilot intends it to.
So it's not as simple as just directly aiming the rotor disc where you want to go.
No, it's not.
There's this whole complex system that translates the pilot's input and accounts for this 90-degree lag.
Right, and it really highlights how sophisticated the engineering is behind something that feels so simple.
Right, like I just push the stick forward and the helicopter goes forward. But there's so much more to it.
There is, yeah.
So the cyclic is all about tilting that rotor disc,
Yep.
which then directs the main rotor thrust and moves the helicopter horizontally.
That's right.
Now, what about dealing with that constant torque? That's where those anti-torque pedals come in, right?
Exactly. Down at the pilot's feet, those are crucial for counteracting that rotational force that's created by the main rotor spinning.
Right.
And, Newton's third law, for every action, there's an equal and opposite reaction.
Yeah.
So as that main rotor spins in one direction to create lift, the fuselage itself wants to spin in the other direction.
Of course, right.
And the tail rotor's job is to stop that from happening.
So the tail rotor is basically a smaller rotor on the tail boom producing thrust in the opposite direction to the main rotor's torque.
Exactly.
Keeping the helicopter pointed where you want it to go.
That's it. And the anti-torque pedals
Mm-hmm.
are what control the pitch angle of those tail rotor blades.
Okay, so pushing on one of the pedals changes the pitch of the tail rotor blades, changes its thrust, and causes the helicopter to yaw.
Which is rotating around that vertical axis.
Yeah. And our source material mentions that pushing the right pedal yaws the nose of the helicopter to the right and the tail to the left.
Correct.
And pushing the left pedal does the opposite.
Exactly. And that's the standard setup for most helicopters, specifically for those where the main rotor spins counterclockwise when you're looking at it from above.
Got it.
Of course, if the main rotor spins clockwise, then those pedal directions are reversed.
Makes sense.
And the tail rotor's pitch angle can be positive, negative, or even zero.
Okay.
Generally speaking, positive pitch is going to push the tail to the right.
Right, to counteract that clockwise torque.
Exactly. And negative pitch is going to push the tail to the left.
Okay.
And the maximum positive pitch capability is usually greater because its main job is to counteract that significant torque from the main rotor.
And so the pedals aren't just for hovering, are they?
No, they're not. Once the helicopter picks up some airspeed, they play a role in longitudinal trim.
Helping keep the nose aligned with the direction of flight?
Exactly. And above a certain airspeed, that vertical stabilizer on the tail,
Right.
that really starts to help with directional stability, which means less work for the tail rotor.
Okay, but I imagine the size and design of that fin must be important.
It is. Yeah, if it's too big, it can block the tail rotor's thrust.
Oh, right, of course.
Or it could make the helicopter weather vane too much.
And what is weather vaning?
So weather vaning is the tendency for an aircraft or a helicopter to align itself with the relative wind.
Okay, like a weather van on a rooftop.
Exactly. And too much weather vaning can make low speed and hover control trickier.
Makes sense. And our source material also mentions helicopters that don't have those traditional tail rotors.
Right, like those with tandem rotors or intermeshing rotors or coaxial rotor systems.
So how do those manage anti-torque and heading control?
So in those unique configurations, the torque from the main rotors is usually counteracted by having multiple rotors that spin in opposite directions.
Oh, interesting.
So for example, in a tandem rotor helicopter, you've got two main rotor assemblies, one at the front and one at the back.
Exactly. And they rotate in opposite directions.
Okay.
And that cancels out most of the torque.
Oh, that's smart.
And then for heading control, those helicopters often use the pedals to adjust the thrust from each of those main rotor systems
Okay.
to create a yawing moment that turns the helicopter.
That's a really clever way to avoid needing a separate tail rotor altogether.
It is.
Okay, so just to recap what we've learned in this deep dive into these fundamental helicopter controls,
Okay.
we've got the collective, which is our primary way to generate lift by changing the pitch of all the main rotor blades together.
Right.
Then we have the cyclic, which uses this really intricate mechanism to change the pitch of individual blades as they rotate.
Yeah.
And that allows us to tilt the rotor disc and move the helicopter in any horizontal direction.
That's right.
And finally, we've got the anti-torque pedals, which control the thrust of the tail rotor or manage that differential thrust in the other configurations that we talked about.
To counteract the torque from the main rotor and give us control over our heading.
Exactly.
And all of that is happening while the pilots also got to manage the throttle sometimes with help from governors or correlators
Right.
to maintain that constant rotor RPM.
A lot going on.
It's a lot, yeah.
A lot of coordination.
It's a really remarkable system
It is.
where each input has this direct and predictable effect,
Right.
but then it also influences all the other systems.
Yeah, it's all interconnected.
So mastering helicopter flight really is about developing this deep understanding of all these primary controls.
And the ability to use them all together smoothly and intuitively.
Yeah, absolutely. Well, this deep dive has given us a fantastic overview of how these helicopter controls work.
It really has.
We've seen how adjusting that blade pitch collectively gives us vertical lift.
Right.
Tilting that rotor disc with the cyclic dictates our horizontal movement.
Yeah.
And those pedals manage that twisting force of torque to keep us pointed in the right direction.
Exactly.
So what does all this mean for our listener?
Well, it means that the seemingly magical ability of a helicopter to just hover in place or to perform these complex maneuvers actually comes down to this really elegant and precisely balanced interplay of forces.
And all controlled by the pilot.
It's right through these three fundamental controls.
It's incredible.
It is.
And think about it, is all of that constant coordination.
Right between the collective cyclic and the pedals.
It makes you realize just how much skill and situational awareness a helicopter pilot needs.
Absolutely. And how much mental work is going on to fly these machines and to pull off those maneuvers we see.
Totally, and we've only scratched the surface here today.
This is just the foundation.
What other questions does this raise for you?
What other aspects of helicopter flight are you curious about now that you understand these basics?
Maybe we can explore those in a future deep dive.
We should.
Thanks for joining us.
Absolutely.
And we'll see you next time on the Deep Dive.